What I'd like to do is talk about some calculations done in quantum general relativity that tell us some things about quantum gravity in a corner of the parameter space. Okay, so it's low energy, low curvature, really low integrated curvature, but that's a strange word. So I'd like to do three things. The first is the introduction. I'm trying out a different way than I normally do, using a comparison to QED, because many of the techniques aren't that much different than QED. I then will go through some generic lessons from some calculations. And my third topic is a novelty, a non-local partner of the cosmological constant. It's a bit more specialized, and I have a sense that I may drop that given what I've learned about the audience today. Also, for discussions here, not just this talk, I'd be interested in talking to people that are interested in quadratic gravity, people that are interested in the arrow of time. In particular, there's an arrow of causality in quantum field theory. It's people interested in higher derivative theories in Ostragradsky, et cetera. So I have a bunch of other things it'd be nice to have whole conversations on. But for us now, the main topic is how we think about quantum gravity. And the way we think about all our fundamental theories has undergone a paradigm shift while we were perhaps not thinking about it. So if you're thinking of even quantum field theory from the classic textbooks, it's probably not how we think about it anymore. We've developed a set of techniques and a way of thinking about it such that we think of all our theories as effective field theories and can do calculations with them. The way we describe the theories, we have a path integral. Path integral quantization is essentially the only useful way to do Yang-Mills and the electroweak theory, QCD. So we quantize using path integrals. We have a local Lagrangian. In that Lagrangian, in that path integral, I have put a subscript lambda. It's a cutoff where physics is an experimental science, and we know the degrees of freedom up to some scale lambda, and we don't know it beyond that. And so this cutoff, using a cutoff in effective field theory, is a rare moment of humility among the particle theorists, a group that's not particularly known for humility. All of the standard model is expected to be an effective field theory with corrections that come beyond that. This is the laws of physics, what's on that slide. Now, and it's a quantum theory to begin with. And in the path integral, you need to have not only the photon, but you need to have the metric also if you're going to even obtain, as the low energy limit of that, the classical physics. You need to, the graviton in the classical limit is still a dynamical degree of freedom, and therefore it lives in the path integral. So we start with a path integral, and we have some knowledge about how to get to a classical theory, though even that's the tougher part. So in a way, I'd like to emphasize or agree with Steve on that it's not that we take a classical theory and do something to it to make it quantum. We really start with a quantum theory and do something to make it classical, to get the classical world. In such a paradigm, general relativity fits actually very naturally. So let me detour into QED and show you some of the things that happen in QED. So QED has a path integral the same way, with a more limited Lagrangian. But even here, there's a cutoff, because the photon field, which I'm doing the path integral over, is not the right degrees of freedom at the electroweak scale. It gets replaced by some combination of hypercharged boson, SU2 boson, and Higgs field. And so beyond that scale, it's not the right degrees of freedom. So even though it could be, it's not. So there's in the measure, there's some sense of a cutoff that we apply it only in limited regions, and our effective field theory techniques let us get away with that. If I go to extremely low energies, we can integrate out and get the massive particle that's in there, which is, let's call it the electron. And so energy is well below the electron. You can integrate that out, do the path integral over it. I'll show you what the answer looks like in the next slide. And you're left then with an effective field theory for just the photon that's valid when you're not asking questions about the electron or the proton or whatever heavy particle you want to put in there is. And the way you do it, the simplest way to set up this effective theory is to match. You do a Feynman diagram calculation. The Feynman diagram calculation in this particular case is the vacuum polarization, though there's also box diagrams, and we could elaborate more. But for my purposes, I'm just doing the box diagram. And at very low momentum, it goes like some tensor in momentum times a power of q squared over the mass squared. It becomes a log at higher energies. You can use that and you read off what is the effective Lagrangian that would reproduce that loop effect. And it is a higher derivative effective Lagrangian. It's F box. F box is what happens if you are trying to get q squared. Box over m squared is that q squared over m squared. And the fact that it's local is important, and it follows strictly from the uncertainty principle. Anything that you see at high energies looks local when you are at low energies. It's also interesting that we have a bias against theories with higher derivatives in it. Yet here, nature has given us one. We know experimentally that this is not producing an instability. So if you know things about higher derivative theories, you know that these are supposed to be unstable, but they're not. These can be used as effective field theories in the region of validity without any instability. However, if I were to do massless fields, I end up with a different pattern. I don't end up with a local effect anymore. Back 2 slides ago when I showed you the calculation, the log q squared, in the limit that the mass goes to 0, you're ending up with logs. And so if I were to do this in this limit, I would end up with non-local effects that, in this case, they're log non-local effects. Notationally, I'm writing this here as f log box f, but that's a shorthand for something where the fields are defined at different space-time points, and there's a function running between them, which is the Fourier transform of a logarithm. So one of the things that you see here is that there are non-local effects at low energies, whereas become local at high energies. This is a function of the uncertainty principle. I'll skip this slide, but if people are interested in making covariant actions, there are ways to do that. But there are even more non-localities that appear surprising. If I just take that same thing and couple up to classical gravity. So I'm not doing any quantum gravity at this stage here. The gravitational matrix element of that has 2 photons, 1 graviton, has a very striking pole. It's a 1 over q squared pole. And if I try to make that into an effective action, it's very non-local. It has a 1 over del squared, 1 over box, with known coefficients that come from the calculation. It's actually related to the QED anomaly, but but that's another story. So let's think of some of the same things in general relativity. If we do, I'm being agnostic here about what the ultimate high energy theory is. I'm only going to look at low ordinary energies. But we don't need to know that. We know how to do effective field theory, where you only use the fields at the energy that you're using them. Well, we do know something about the high energy effects. The only thing we use really is that they're local when viewed from low energy. So we use the uncertainty principle. So we would order the Lagrangian in the derivative expansion. I should have probably kept the cosmological constant in that there's a zero derivative term, which is the cosmological constant. There's the Einstein action, which is 2 derivatives. There's curvature squareds, which are 4 derivatives, et cetera. These other new terms that I've added are consistent with the symmetries of the theory, which is general covariance. But they're also essentially very negligible at low energies. But we could not make any statement about them aside from the fact that they are local. However, you can still get non-local effects. So effective field theories are techniques don't predict those coefficients at all. They're unknown as far as the effective field theory is concerned. But low energy effects come from propagation of the light particles in the theory. Much like we saw, if I took the mass of the electron to 0, I got this logarithmic non-locality. And that shows up in calculations by various effects, logarithms, and actually we're going to get a square root in just a minute. Square root of q squared, non-analytic functions that couldn't be expanded as an effective Lagrangian. So in the picture that you're seeing there, I don't have a good pointer. The last line there, if I look at something that has just the power of q squared correction, so this is, imagine, a correction to something that we have calculated. The term that's proportional to the q squared is some like higher derivative term. It's a local term. But the logs and the square roots are not. And so they are the unique low energy predictions. So that was the introduction. If I'm going to now do couple calculations for you. There's more I could do, but I'll just do a couple. So I'm going to argue that we have a way to do calculations at low energies. It's valid in some domain, and the domain will be an issue that we will talk about. And so we've been waiting for a quantum theory of general relativity for a long time. What does it say? Now, I warn everybody who's going to ask a question about, are these experimentally observable? Things I will tell you are not. They're too small to be observed. But in a way, if I try to put a positive spin on that, perturbation theory is an expansion in a small parameter. This is the best perturbation theory ever. Okay, but it doesn't matter. This is what its general relativity says in the domain of the effective field theory. The trends are interesting. So one of the things that we can do is look at the quantum correction to the non-relativistic Newtonian potential. That has classical corrections due to general relativity. It also has quantum corrections. And it's a type that I just told you about. The leading Newtonian piece is one graviton exchange. The square roots and the logs come from loop diagrams. I might as well just show you the picture. Those are the pictures of the various diagrams that are involved. They're Feynman diagrams. And the original calculation was done in the painful way that Clifford had mentioned of writing out those Feynman rules with enormously horrendous structure. But anyhow, once you identify the square roots transform into a correction that's a classical correction to the potential, GM over R. It follows from Einstein's theory, but we're taking the classical limit here by going to the non-relativistic limit. So we get the classical correction to Newtonian. We also get a quantum correction. The quantum comes from the logs. That quantum comes with a fixed coefficient, and so despite what we hear about the non-renormalizability theory, that's a correction that we can calculate. And then the local piece, if you see, it's the term that I call Q squared. Q squared over Q squared is a constant. It transforms to a delta function. It gives nothing in this expression. So but one interesting thing is that this is universal. It doesn't depend on the mass. It doesn't depend on the spins. It's a universal feature. Another interesting feature is that by doing Feynman diagrams, I've gotten the classical correction. So the square root is a classical piece. And so part of taking the classical limit from this path integral treatment is I need to have those diagrams in my theory in order to get the classical physics out. But as Clifford again mentioned, this by itself is also now an industry. When you combine this insight with some of the very efficient techniques that he described, you can actually do a very fine classical expansion by doing what is basically field theory. Scattering amplitudes end up producing a lot of interesting classical results. And so the fact that you're doing field theory is not doesn't preclude the use of it in classical physics. Moreover, again, I'm referring to his nice talk, we can get these quantum effects strictly from on-shell amplitudes, which means they're classically well defined. And basically there's another technology of using unitarity. Basically the logs and the imaginary parts of amplitudes come tied together. You do this, you don't need to do any fancy Faddeev Popov ghosts. And you can use the techniques that he described about gravity being the square of a gauge theory to make your on-shell amplitudes very simple. And so this was especially a shock to me when I first did it. The original calculation of that Newtonian potential correction is enormously painful. This is pretty easy. I basically write out a QED amplitude. I multiply them together, and I do a slight lookup table, and I'm done. You can also do it as a dispersion relation. Again, on-shell amplitudes determine the long distance corrections because it is long distance. This actually explains the universality. The universality was found first by my colleague Barry Holstein, Andreas Ross, just by doing a lot of calculations. But this explains it because the tree amplitudes that you start with there have been known for decades to have low energy universality soft theorems, starting off with Francis Lowe's low energy theorem. And extended into gravity. And it's the fact that you get the classical and quantum effects from the same tree diagrams actually explains the universality of this result. However, not all things are universal. If you were dealing with massless particles, so not the non-relativistic system, but an ultra-relativistic system bending around the non-relativistic object, we can get this by using Nyquil approximations where we define the bending angle by the peak of the Eichmann phase. Anyhow, it's a technicality, but it's a well-defined quantum calculation is what I really want to say. Again, you get, by doing Feynman diagrams, you get the first two terms, so I'm doing one loop Feynman diagrams, first two terms of the bending angle that you get from general relativity, so you get the classical results as well as quantum results. The quantum result, however, has different coefficients depending on whether you're doing a massless scalar, a massless fermion, a massless photon, or a massless graviton. And so this is not universal. So the propagation of massless particles past in a gravitational field is not. These effects, now remember they're massless, these are sort of like tidal effects. The gravitons in those loops propagate long distances. And so you're not just sensitive to the metric at some particular point, you're sensitive to it over a range of points. And there's also, obviously, a spread in the bending angles. So some things we can learn, just even from these two calculations, but also from others, is that the parameters, G Newton and lambda, are not running parameters when you're describing physical reactions. I can show you this in more technical detail, and in some sense I do in this slide. If I was to try to renormalize the cosmological constant now due to a loop of a massive particle, I can do it in these techniques. I know how to renormalize. And if I do that, I can do it by, again, by matrix elements expanding around flat space, because you're just talking about the coupling of a field to a quantum loop of a scalar. I do it with the diagrams that I've shown there, and I get a piece that does renormalize it. It's 1 over epsilon is the dimensional regularization parameter, but they don't depend on the external scales of the problem. And then I can also do this by looking at physical reactions and just looking to see if I could come up with some running parameters, and there's not. In a way, you can see it from the calculation I did of the massive and massless ones. They don't have the coefficients that agree. So there's not a good definition of running coupling constant. Oops, sorry, wrong direction. There is you can also find out that there's no quantum corrected metric. When you're even in this low energy limit, you might think that I should just use a quantum metric. That doesn't work. You can see it by just the answers don't agree. You can see it also by diagram, the diagrams that I looked at. Some of them depend on the external particles, some of them don't. You can see some of those in the pictures yourself. Some would be a quantum corrected metric, some would not. All these enter at the same level for the quantum effects. As I said, they're tidal effects. They can't be removed. It's not like you're moving in a metric. You're moving in a metric you're sensitive to lots of different positions in a complicated way. There are no test particles. If you make things very light, you get that massless particle calculation, but they all gave different results. And I wrote mea culpa here because I, in fact, have a paper calculating a quantum corrected metric, which is unfortunately wrong. Okay. Light cones are ill-defined. You see that from the calculation that I showed you too. Gravitons and photons obey different trajectories, so you can't assume that you can map out space-time. Penrose diagrams that we often start our discussions with they have an unknown uncertainty. They're not a controlled approximation in a quantum theory. Thank you, very good. They lead to a global causal uncertainties because we can't identify where the light cones are. Anyhow, so some of the things we would do naturally don't hold even in this low energy approximation. Now, of course, these effects are small at low energies, but as you get higher energies, they get bigger. And so these are uncertainties, they're not controlled approximations. And we can do for gravity what I did in the case of QED before. You can make non-local effective actions where the logs are written in this quasi-local form. This is non-local. This was done by Barvinsky and Vilkovisky. There are these log corrections, and there are also pole corrections like I showed you in QED. So, since people have been giving quotes, this is a fun one. There's a bit of a joke in this one. So it's Frank Wilczek complaining about some of the stuff that's been written about quantum gravity. But he then says, there's a perfectly well-defined quantum theory of gravity that agrees accurately with all experimental data. The joke is that the experimental data, the predictions are tiny and the experimental data is impossible to see the predictions of this well-defined theory. But the part that's not a joke is that we have a perfectly well-defined quantum theory of gravity. So it's valid in some region. That's what he's referring to when he says this. I think, so my next topic, and I'll just really flash through this. This is the bit more technical one, but one of the things I've shown you is these log non-localities that you get naturally. The ones that are well known are very tiny because they're second order in the derivative expansion. They involve curvature, and log box. That's non-local, but that's at order curvature squared, so it's tiny. But there are similar ones at first order, which are two derivatives, so it's competing with just the Einstein curvature, and zero derivatives, which are competing with the cosmological constant. And the question which I never understood till recently is, what are they? I mean, in some sense, you know that they're there, but how do you express them? And the calculation involves the diagrams that I showed you, so for the cosmological constant, the zeroth order in the derivative expansion. It has no derivatives in it. The first two diagrams on that picture up there don't depend on the external momentum in any particular way. Those are just constants. The third diagram is not a constant. It depends on the momentum flowing through there, and that's where the non-locality comes. There's going to be a log non-locality in that diagram. If you calculate the amplitude, the leftover piece after renormalizing the cosmological constant is in that first line up there. I don't mean for anyone to know it particularly, except that you see there's a 1 over q to the fourth, so poles. But the numerator is also q to the fourth. So it's zeroth order, the derivative expansion, and it's multiplied by something which is a log. So there's in momentum space, there's the answer. In position space, if I do it as a weak field approximation, it's field, so I've chosen a particular gauge here so that because it gets rid of some of the crap that you see in that calculation. In this gauge, it's field, log box, field. Gravitational, H is the gravitational field in this calculation. Okay, if I follow Barvinsky and Vilkovisky and make this into a covariant piece, I get the bottom line, 1 over box R, log box, 1 over box R. Zeroth order in the derivative expansion, but very strange. Anyway, I'm going to stop that. Oh, the thing I did want to say is this has an enormous numerical advantage over the cosmological constant because its coefficient is fixed. It's not an unknown parameter. And the cosmological constant itself is extraordinarily small. This is a normal order, but the cosmological constant is too small, is way small. If I just take its coefficient, compare it to the cosmological constant, there's a factor of 10 to the 56. However, it starts at the operator starts at order of the field squared, so it has a bit of a disadvantage there. And I was going to tell you about some calculations looking at it, but suffice it to say, I haven't come up with something earth-shaking, or else I would have published it. I do want to spend some time on this issue of the limits of the effective field theory, because effective field theory, by its definition, has limits. The obvious one is the high energy. As we said, physics is experimental science. We don't know what's happening at high energies. But moreover, the theory by itself tells you it's falling down there. The unknown physics from high energies gives you local terms. Those local terms give you momentum when you take matrix elements, and those momentum get bigger and bigger as you go to higher and higher energies. So everyone, I think, agrees that the theory falls apart at high energies, or could fall apart at high energies. At least the effective field theory does. There is also a possibility that it falls apart in the extreme infrared. And maybe this is different than we often see in effective field theories, but then we often don't take extreme infrared. Maybe it's just a technical problem that we don't know how to solve. But so the metric has the field in it. The metric itself, the field of the metric, gets big even if the curvatures are everywhere small. And you can see this because the gravitational field is built up. And so what I've written there is just a particular example. If I describe the metric using a Riemann normal coordinates, even if the curvature is small, if you take the distances large enough, those corrections become of order 1. So most of the time you don't see that. And we don't have good tools to handle it. The effect is that the field that we're dealing with is the gravitational field. The curvature is another parameter. The curvature can stay small and the field can get big. You also know that from the fact that if I go from infinity to a horizon on a black hole, my field has gotten big, but my curvature may not have. For big black holes, its curvature is tiny. But nevertheless, the comparison between infinity and the horizon, the field has changed a lot. So in some ways, it's the integrated curvature, which is the calculational expansion parameter. We don't know how to handle that. We also don't know how to handle propagation past black holes. And so there are things in the extreme infrared which we don't understand. But ordinary energies seem to work okay. And since some of the focus on this in the conference is on the quantum part of it, you should also notice that, or acknowledge that our knowledge of quantum mechanics is also an experimental science. And we've really tested it relatively limitedly. There could be places where our standard calculations fall apart, and so we should know that in our effective field theory. Anyway, here's my summary. We have a quantum theory of general relativity, which has a particular form of effective field theory, and although it's really not that much different than many of our other theories, and we know how to pull out predictions from it. There are some lessons we've learned from that. There are obviously more lessons to extract, and even more development of the theory, I think, is warranted. And I skipped over much of the novelty. Okay, thank you very much.
John, for a stimulating talk. So do we have any questions? One back there, and then...
Thanks, John. This sort of second point you had in the conclusions about maybe there's an infrared breakdown of EFT in gravity, I was wondering, can you pinpoint something that you think would happen differently in gravity that wouldn't happen in QED, for example, in the far IR?
Well, it wouldn't happen in QED. Actually, I did sort of mean to say that it's not that dissimilar from what happens in QCD. In QCD, the theory is also a perturbative theory on some scales. And as you go to more and more infrared scales, the fields get larger because of the running coupling. And that changes the whole structure of the theory. You end up in a non-perturbative infrared regime. And even though in our physical world, the field strength tensor for QCD is 0, we can't use quarks and gluons as our dynamical variables. So it's not unknown. It just means that you enter a strong coupled portion of the theory and our techniques are limited. Now it's possible that for general relativity there's something bigger going on, but I don't know the answer to that. It's something that we know can exist, and I'm just pointing out that there is something in general relativity that has the same feature.
Yes, hi John.
Yeah, hi Renan.
Thanks.
There you go.
I have a couple of questions. So you said, well, I have a perfectly viable theory of quantum gravity.
Right.
But you also said, of course, the effects, that was one of your health warnings on the first slide, are tiny and not measurable.
Right.
So is it possible that it's not even in principle falsifiable as a theory?
It's not, did you say quantizable or quantifiable?
Verifiable. Verifiable.
Okay,
Falsifiable.
Yeah, falsifiable. So what I've been explaining are the conventional predictions of quantum general relativity. They could be false, but that means you're giving up something of that starting point that I said. You're giving up either the quantum mechanics part or you're giving up the relativity part. These follow from that starting point. So I don't expect those particular predictions to be verified in my lifetime.
Well, yeah, but there could be more than the effect is just very small and we are just not ingenious enough to devise experiments. But I mean more like, difficulties of principle that people have raised, with, can we measure individual gravitons? So, or are there subtleties, in gravity that are not present, in QED?
I grew up as a particle phenomenologist doing non-renormalizable theories of pion physics. This has all the same flavors of that. Really, the calculations are identical to pion physics calculations. And pion physics calculations have been experimentally verified. So the framework works. If we give up, but there are assumptions. So the assumption is that it's a four-dimensional world, there are no wormholes, there's
this is just high energy.
but I'm not going to actually come up with a way that I could violate it. Let's imagine we have make a two-dimensional analogy. Here's the two-dimensional world that folds back on itself and comes very close to each other when it's folded back on itself. So it'd be like a wormhole from one place to another. I can come up with wild and crazy ways to do that. But within the set of assumptions that I've laid out there, it's a four-dimensional world with a local Lagrangian and a path integral that's valid in the region of parameter space. Then that's what it is. If we were somehow able to show that these results were not correct, we would give up something of that.
So connected to that, for instance, you quoted this universal result, right? The gravitational potential.
Right.
So that's a very interesting story. So what I've always wondered, there's of course a little r in there.
Yes.
what's the operational definition?
Yeah, that's a great question. There is, of course, in general relativity, an ambiguity is what you call R and what you call P. And the Einstein-Infeld-Hoffman calculations show an ambiguity of that in the classical case, where changes in what you call R and changes in what you call P are...
You mean momentum?
Are related in a particular way. They're actually the same ones come in the quantum one. And so there is a particular definition that we're using here where the R is the same as in some classical calculation, which has that potential, and it has a particular lack of a quantum correction. Okay, so there's a particular place, it's the GR over times P squared term is absent because it is not generated using these coordinates.
But the R is a coordinate R in this setup.
The R is...
A coordinate R. So
it's a coordinate
if
R,
I
yes.
say operation, I'm asking you to make it, is this an observable in the
Right.
sense of...
Yeah, so, if you push me really hard on that, I would go back to momentum space and use this potential to do a scattering amplitude as a function of angle or something like that. And since I'm in near asymptotically flat, the angles would be well defined. And so, I got this by taking a scattering amplitude. And technically what I do is I go to non-relativistic limit in Fourier transform. So R is the Fourier transform coordinate. But if you push me, I'm going to go back to momentum space and calculate something that's an asymptotic scatter.
Infinity. You sent me to infinity.
Yeah. I'm going to actually, yes, that's...
So maybe, is this really an observable?
Well, I think it's as observable as electromagnetic scattering is. I mean, in principle.
Here we are talking about gravity, which we know has an effect on space-time.
Yeah, but in this level, it's really just a scattering amplitude near Minkowski space. You send two particles in from flat Minkowski asymptotically, they interact and come out. Okay, that's all the calculation has been. The techniques that I showed there are the same that you can calculate a second order electromagnetic potential at one loop using exactly the same techniques. And you would get you get the electromagnetic Coulomb scattering and you get finite corrections to it. This is as observable in momentum space as QED is.